Okay, guys, this week we're talking about hypothesis tests for the mean. There's two types. You should already know what they are based on the confidence intervals we did 2 weeks ago. If we know sigma, we're going to have a z-test. If we don't know sigma, we're going to have a t-test. Remember, sigma represents our population standard deviation. So today we're just going to be dealing with z-tests. Same old requirements, nothing's changed there. Simple random sample. We have to know the population standard deviation for the z, and either the population is normally distributed or n is greater than 30. So we're just going to deal with these. We're going to assume they're true if it doesn't specify. We might look at some data and it might not specify that it's normally distributed, but all the problems I'm going to give you, they're going to be satisfying these requirements, so just don't worry about it and work them. The only thing that's changed from last week is how we calculate our test statistic. It's a slightly different formula than the P test statistic. We're going to take our sample mean, subtract the population mean, divide that by the population standard deviation over square root of n. That's that central limit theorem there. But again, we're going to use p-values and critical values, so everything else from after calculating the test statistic is going to be the same. So we're just going to work a few examples today, and we should be good to go with that. So if you did well last week, this should be a breeze. If you didn't do so well last week, you're going to have to relearn all that stuff again. But yeah, the only thing that's changing from last week is the test statistic, how we calculate it, and on Wednesday, we're going to be looking at t-tests, so we'll use the t-table instead of the z-table on that one. But other than that, everything's the same. So let's jump right into an example. So we've got 13 red M&Ms from a randomly selected bag containing 465 M&Ms. The standard deviation of the weights of all M&Ms in the bag is 0.0565 grams. The sample weights in grams are listed below, and they have a mean of 0.8635. The bag states the net weight of the contents is 396.9 grams. So if we divide that by the 465, the number of M&Ms in the bag, we get 0.8535 grams in order to provide the amount claimed. Use the sample data with a 0.05 significance level to test the claim of a production manager that the M&Ms have a mean that is actually greater than 0.8535. So consumers are being given more than the amount indicated on the label. We're going to use the p-value method for this one. And again, n is less than 30. There's 13 M&Ms here. But if we did generate a histogram for this data set, then we'd see it's normally distributed. We're good to go. I'm not going to worry about the requirements on these, just do them. In real life, we would have to worry about the requirements, but not today. First thing again, start with your hypotheses, your null, and your alternative. Okay, let me go back and read what the claim says. Production manager, that the M&Ms have a mean that is actually greater than 0.8535 grams. That's the claim. So we need to decide, well, is that null or alternative hypothesis? Greater than, that makes it right here. So what are we dealing with? We're not dealing with P, that's proportion. Instead, we're dealing with the mean. And if you remember, mu is our population mean. So mu greater than 0.8535 is the alternative, that's also the claim. That means mu less than or equal to 0.8535 is the null. So now we're going to write down all of our information. So N, we're just looking at this sample here. We're not looking at the whole bag of M&Ms, so the N is 13. X bar, I believe they gave us that. The average weight of this sample data was 0.8635. Now, since we have the data, we could calculate that, but they were nice enough to give it to us, so we don't have to. On the TIs, you can just type in the data set, and you just select data instead of stats, and it will generate you the hypothesis test. We also know sigma, it's a Z, so we have to know sigma is 0.0565. Then we have our alpha, our significance level, 0.05. We know mu, gives it to us right there, 0.8535. So if we look on the formula sheet, geometry, there we are. If we look on our formula sheet, we're right here. The test statistics are all right here. We're going to be using these three. Today we're using this one. Mean with a population, one population with sigma known. That's what we need to do. Okay, so I just stick that over here on the side. So let's check. X bar, yup. Mu, yup. Sigma, N, got it. So now we can calculate the test statistic. So again, it's a Z test statistic. Because we're dealing with a Z test. Sigma is known, we use Z. If sigma is unknown, we're going to use a T. So X bar is 0.8635 minus the mean, 0.8535. That decimal should definitely be further out. Over sigma, 0.0565 over square root of N, 13. So this is our test statistic. Just need to type it in the calculator and see what it is. I use the Casio, 0.8635 minus 0.8535 over 0.0565, and that's over the square root of 13. So this is our test statistic. Turns out to be 0.63, etc. Again, I'm going to store that value for later. And let's just check. There it is. That's my test statistic. If I'm using the chart, I'm going to go ahead and get 4 decimal places using the p-value. I don't only need 2. So 0.6382, just to be safe. That way, whichever way we do it, which we're going to do it both ways, by the way, we'll be good to go. So I'll start with the traditional method, finding my critical values and sketching my curve. So I've got that. To get my critical values, I need to look at my tail. It's a right tail. So I'm going to look up alpha on the chart and use the positive. And for 0.05, our z-score is 1.645. So that's going to be our critical value. The test statistic and the critical values are both z-scores. All of these things in these columns plus rows are z-scores. You have to specify the difference between a test statistic and a critical value. A lot of y'all were getting confused with that on the test, talking about the z-score whenever there isn't a z-score. There's multiple you have to specify. So our critical value is 1.645. Let me sketch it. My beautiful artwork here. And the center of your curve is always 0. Always. Our critical value, I'll stick it right there, is 1.645. It's a right tail, so I'm going to show you to the right of that. Okay. Now for the test statistic, let me go ahead and just put it in red, make it easy to spot. Well, test statistic will be in red. 0.6382. So, right, 0.6, and it doesn't matter between here and there, right? The important place where to put it is either between outside of the rejection region or inside the rejection region. That's what matters. You don't have to be precise with exactly where it is. 0.6382. All right. If we have our test statistic outside of the critical region, the rejection region, we fail to reject the null. So that's our initial conclusion. We fail to reject the null. That's the traditional method. I'm going to do the p-value method now. To calculate the p-value, we do have that nice little flow chart if you don't remember things. First, we decide what kind of tail we have. We have a right tail. That means we need the area to the right of the test statistic. There's my test statistic. To get the area to the right of that, I'd look it up on the chart. Now, you could also do both the critical values and the area in your calculator, inverse norm, normal CDF. That's way back from the normal distribution. You should know how to do that. Anyway, I'm going to look at 0.64 on the chart. 0.64 right here. So 0.7389. So let me just do this p-value in purple. P equals, and I'm going to write down that 0.7389. But remember, you have a right tail. Our flowchart just told us we got to get the area to the right of that. The table always gives us the area to the left. So we're going to have to do 1 minus that number. That's going to be 0.2611 for our p-value. So the p-value test, we compare it to alpha. P is greater than alpha. So we fail to reject the null. There's my alpha. That's P. This one's bigger. Fail to reject the null. So either way you do it, you'll get the same initial conclusion. So then our final conclusion would be, well, if our claim's in the alternative, we fail to reject the null, so there is not enough evidence to support the claim that, and whatever they said the claim was, M&Ms have a mean that is actually greater than M&Ms have a mean that, where'd you go? That, come on now, is actually greater than 0.8535 grams. So that'll be our conclusion. So there's not enough evidence to support the claim. That's the main part right there. Not enough evidence to support the claim. Our claim was in the alternative. We failed to reject the null. Not enough evidence to support the claim. What was that claim? We got some fat M&Ms. So now on the calculators, I do Casio. To get your critical value here, we just use inverse norm and look up our alpha value, 1.645 right there. To get the p-value, we need the area to the right of our test statistic. So we do a normal CDF. That would mean our test statistic was our lower bound. Our upper bound would be infinity. And leave those alone. 0.2617. 0.2611 is what we got from the chart. Again, the technology has more accuracy. It has more decimal places it's working with. But it's still not exact. It's not perfect. So that's how you get the p-value of the critical values. TI users, as you can imagine, once you write down your information, you're pretty much done. Go to stat, tests. What kind of test are we dealing with? A z-test, number one. Do we have data or do we have stats? We have both, actually. So we could select data and type in all this mess right here, but that would take longer, so we're going to just type in the stats. Mu is 0.8535. Sigma is 0.0565. X bar, 0.8635. N was 13. What kind of tail do we have? Let's look at our alternative. We always look at the alternative for the tail. It's the greater than. And it gives us this. Z is 0.6381. Well, 2 if we round, so yeah, we got the same thing there. P is 0.2616. Yep, if we look down here, that's what we got. Here too, 0.2616. 0.2616. And then that's it. You have your information, you can reject the null. Or fail to reject the null in this case. Next. Did I duplicate that? Apparently. Oh no. Okay. So this is a different problem. It just looks very similar. We got 27 blue M&Ms with a mean weight of that. The sigma is known to be the same thing, so pretty similar. I got this from the homework set. It is extremely similar to the example problem. So write our conclusion or our hypotheses. Let's see. Claim that the mean weight of all M&Ms is equal to whatever that is. We have the weight is equal to. That makes it a null. That goes in the null. Equality always goes in the null. That means our alternative is not equal to, which by the way is a two-tail test. So if you're doing this without a TI, make sure you take care of that. TI does take care of all that for you if you select two-tail. Let's write down our information. N is 27. X bar is 0.8560. Same sigma here, 0.0565. Alpha, again, is 5% significance. And we got what we need. Grab this. That's the form we're using. I can write down mu again. I have it right here, but I'll write it over here as well. That's a terrible mu. Now, calculate our test statistic, and then do either a traditional or p-value test. On this one, I'll just, well, go step by step. Part A, what's the test statistic? That should be your first step always. So Z equals X bar. Now, when you're doing these on your own, actually write down this step. Don't just type it in the calculator, because if you screw up, you'll actually be able to see what you should have written. Take the time to write it down. .0565 for the standard deviation, square root of 27 underneath that. Again, I'm just going to do this on the Casio for two reasons. It's easier, and, well, TI, you can just use the Z-test. 0.8560 minus 0.8535 over another fraction, 0.0565, and square root of 27 on the bottom. So I get a test statistic of 0.2299. There's part A done, test statistic. Test statistic. What are the critical values? I'll get those in blue. Alpha is 0.05. It's a two-tailed test. Remember, two-tail means we cut alpha in half, among other things. But right now, for critical values, we cut alpha in half. So I'm going to look up 0.025 in the chart, or inverse normal 0.025. 0.025 right here. So that's negative 1.96. Two tails, we have both the negative and the positive for our critical values. And we could go ahead and do our curve sketch and see if we reject or fail to reject the null. In fact, I'm going to do that. Curve sketch, zeros in the middle, negative 1.96, 1.96 for our critical values, shade, either tail for two tail. Test statistic goes right here. And we actually do want to look at the curve sketch for the p-value as well, because whenever we have a two-tail, we have to decide if the test statistic is to the left or the right of our center. I mean, you can kind of, it's obvious if it's positive to the right, if it's negative to the left, but just sketch it out so you can see it. So we would, in fact, fail to reject the null here. Okay, what else? What else? It says, what's the p-value? So we'll do that in this nice green color here. So P. Let me grab my flow chart, see what's going on. So two-tail, and again, we found that it was the right of the center. It's the right of the center. So we're going to find the area to the right of the test statistic and double it. It's twice the area to the right of the test statistic. We need to find the area to the right and double it. So I'm going to look up first this test statistic, 0.23. 0.23, that's 0.5910. I'm going to do 1 minus that, and that's going to give me 0.490. However, I have to double that because we have a two-tailed, and that's what the flowchart told us to do. Twice the area divided the test statistic. So if I double that times 2, that's going to be 0.8180 for my P. And that's a good bit bigger than alpha. So yeah, we're going to fail to reject the null in both of these cases. So we fail to reject the null as part D. You can base it on either the curve sketch or the p-value. P is greater than alpha, we fail to reject the null. The test statistic is not in the critical region, we fail to reject the null. Now we're ready for the final conclusion. Let's look back. Our claim is in the null. We fail to reject the null, so there is not enough evidence to reject the claim that whatever the claim was, the mean weight of all imminence is equal to that. The mean weight of all m is equal to 0.8535. That's it. So if you don't know how to get this statement right here, you need to go back and look at this chart. Let's see. Okay. Depends on where the claim is, the null or the alternative, and whether or not we reject or fail to reject the null. That is what you use to write your conclusion every single time. So in this case, our claim was in the null, we failed to reject the null. That's why claim in the null, fail to reject the null, there's not enough evidence to reject the claim. I saw a lot of you supporting whenever we had our claim in the null. You can't do anything with supporting or not supporting whenever the claim is in the null. I saw you reject when the claim was in the alternative. We don't reject when the claim is in the alternative. We either support or there's not enough evidence to support. We can't reject it. So make sure that you pay attention to where your claim is and then whether or not we reject the null. Okay, here's one, and this one, I don't think they give us the stats. Nope, we're going to use the data. Okay. So, 14 different second-year medical students at Bellevue Hospital measure the systolic blood pressure of the same person. Oh yeah, they keep using these same scenarios, don't they? Assuming the population standard deviation is known to be 10, use a 5% significance level test to claim that the mean blood pressure is less than 140. Hypertension is defined to be blood pressure that's too high because it's 140 or greater. Based on the hypothesis test results, can be safely concluded that the person does not have hypertension. So again, no matter what, the first thing you're going to do is write down, yes, actually write down your hypotheses. Take the time, get the pencil and paper out, and write it. So, does not have hypertension. Basic claim that is too high because it's 140 or greater. That the mean blood pressure is less than 140. So that's our claim right here. So we're not testing 140 or greater. That would be testing if they do have hypertension. We're testing if it's less than 140. So find the word claim and then read. Claim that what? The mean blood pressure is less than 140. Now it is less than, so that goes in my alternative. And that's my claim. That makes my null greater than or equal to. Now, n is 14, that's pretty obvious. Sigma, they give us that, is 10. Alpha is 0.05, so I'm just going to go ahead and grab this formula and, oh, wait, what are we missing? We're missing x bar, aren't we? So we have a set of data, and we need to find the average. You should know how to do that. Out of all the numbers, divide by how many there are. You can also type them in the list on either calculator, and it'll give you the average if you go to the proper settings, proper program. So stat is where we need to be. So mode 3, one variable. Then we're going to type in all this information. So I'm going to do this one on both calculators, but any other data problems, I'm just going to do on one. 138, 130, 135, 140, 120, 125, 120, 130, 130 again, 144, 143, 140, 130, and lastly 150. Okay, 14 numbers in there, so that's good. I'm going to hit AC to get to the main screen here for stat. I'm in mode 3 right now. Type in all that information. Don't go back to mode 3 because you'll erase all your data. From here, we're going to go to shift and then number 1. What do we need? We need some variable. We need some mean. That's number 2 right here. It equals, and there it is. And if you want, you can store that for later use. May or may not need it. You will whenever we type in this formula. So yeah, I'm going to store that to A. 133.9. Remember your rounding rules. Our data goes to the ones place. We round one place further, so to the 10th place. X bar is going to be 133.9. Now we have the information we need to calculate our test statistic. X bar we just calculated was 133.9. However, in the calculator, I'm actually going to use that whole decimal they give me because I stored it to A. 10. And let's see what that comes out with. So I need to go to mode 1. And I'm going to do fraction. Let me just check, just to make sure. 133.9, yeah. Okay, we're good. I'm going to do A minus 140 over another fraction, 10 over square root of 14. Negative 2.2717. That's my test statistic. I'm going to store that. Now, I'm going to actually store this to B because I already have my mean stored to A. I don't think I'll need it again, but if I do, I'll have it. So there's my test statistic. It doesn't specify how to do this problem, so I'm just going to use the p-value method. So to do the p-value, we're going to calculate the area based on the tail. Look at your, not geometry. Look at your flow chart. It's a left tail. So we're going to calculate the area to the left of the test statistic. So I just need the area to the left of this, negative 2.27. So 2.27, I think this is it. Yep, 0.0116. And that's my p-value. P is less than alpha, so we're going to reject the null. We rejected the null, the claim is in the alternative. There is enough evidence to support the claim that the mean blood pressure level is less than 140 millimeters of mercury. Okay, that's how we do it on the Casio, slash with the charge, slash, whatever. And again, you can use the normal CDF to get the p-value instead of looking it up on the chart. Now, TI users, this is for you. I'm actually going to type all this data in again. So to do that, the first thing we do is type in this data. Stat, edit. And then just clear that list, go to the top, hit clear and enter, and there we go. 138, 130, oh, I hate that. 130, 135, 140, 120, 125, 120, 130, 130 again. This 144, 143, 140, 130, 150. And we do have 14 values. So that's, I always like to check and make sure I have at least the right number of values. That way it's less likely that I screwed up somewhere and doubled something. So I'm going to go to stat, test, z-test. This time though, I'm not going to select stats, I'm going to select data. So which list? List 1. What's my mean? 140. Standard deviation, 10. List, I put mine in list 1. I suggest just always typing in list 1, make it easy. Frequency never changes. That's going to be 1 for us. It's a left tail though, so let's change that. And calculate it. Test statistic, p-value, the mean. So we got everything we need. Again, P is less than alpha, we reject the null, the claim is in the alternative, so we support the claim. Next example. Okay, the population standard deviation for waiting time to be seated at a restaurant is known to be 10 minutes. An expensive restaurant claims that the average waiting time for a dinner is approximately 1 hour. But we suspect that this claim is inflated to make the restaurant appear more exclusive and successful. A random sample of 31 customers yielded a sample average waiting time of 50 minutes. Is there enough evidence to say that the restaurant's claim is too high? So, we are testing to see that the restaurant, if 1 hour is too high. Okay, so it claims that the average waiting time is 1 hour. So if we want to test just for too high, we could test if the average waiting time was greater. So 1 hour goes here for sure. Depends on how you want to look at it though. A couple ways you can approach this problem. So we can either say that the mean is 1 hour and test that, but that would just mean it's going to be different from 1 hour, but we want too high. Okay, so we're actually going to claim that it's about 1 hour. So let's test, instead of being 1 hour, let's test if it's less than 1 hour, which is 60 minutes, of course. So we're going to actually test if the wait time is less than 60 minutes. So we could also test the is 1 hour thing, but we can reject their claim, but we could support this claim. Either one of these would be appropriate. So this is one I kind of pulled from the internet to kind of give a real life example of how we can interpret these results. So I'm actually going to show you what both results would say, and you can decide from there what you like better. So we have 31 customers. Also, the book they were using said n had to be greater than or equal to 30 to be normally distributed. So I had to change that to a 31 for us because it doesn't say anything about normally distributed. The population standard deviation is 10 minutes. X bar was 50. Okay. So we're going to have that saved. Yep. Calculate our test statistic based on an alpha of, well, I guess they leave the alpha up to us. So we're going to start with an alpha of 0.05 and see what happens. That's why I like the p-value test. You can see exactly how sure you are of whether or not you're going to reject it. Because if we have a p-value of, let's say, 0.25, then we'd reject it for an alpha of 0.5, but we wouldn't reject it for an alpha of 0.01. So we, it could go either way on that one. But if we have like 0.0001 for a p-value, we're pretty certain, no matter what, that our claim is true, that we reject the null. Now, let's just get to work. I'm going to do 50 minus 60 over 10 over square root of 31. Let's see what we come up with. I'll use this one. And I got myself in the way here. Hang on. Okay. Go mode 1. So I'm going to do a fraction 50 minus 60 over over 10 over the square root of 31, and that gives me negative square root of 31, which can be, negative 5.57. Store that. What was that again? Negative 5.57. So I'm just going to do the p-value on this one. So to get the p-value, it's a left tail. So I'm going to get the p-value for both the left tail and a two tail, just to see what they look like. So using the chart, negative 3.5 and lower has an area of 0.0001, and that's being generous for this one. The p-value from the chart would be 0.0001, and if we had a two tail, we'd have to double that. So 0.0002. Let's actually look on the TI though and see what happens if we get that p-value, because it actually calculates that area. So 60, alpha of 10 minutes, 50 for X bar, 31 for N, and we're going to do the left tail first. Yeah, it's got 7 zeros followed by, it's a decimal, 7 zeros and a 1. That's a really tiny P. Okay, let's see. What if we do a two tail? How sure are we then? Okay, that one only has a decimal followed by 3 zeros and then a 3. Either way, peeps, we're rejecting the null. T is less than alpha. We reject the null. That restaurant's lying. So we could say there is enough evidence to support the claim that the average waiting time for the restaurant, if I spell that right, is, and actually this is our claim on this one, less than 60 minutes. So that's how we were going to go about seeing if the restaurant's claim is too high. The way this question was worded is very convoluted. If we read it here, we look at a two-tailed test. Reading it here, though, it just says too high. So if in actuality we wouldn't care if it was too low, so we actually have to look at a left tail test, a less than, based on what this is asking. Of course, either way we do it, we're going to say that that restaurant's lying. If we had a two-tail test, as you saw, P is still going to be less than our alpha. Even if we had a 0.001 alpha, that would still be less. So we would reject the null, and the claim would be null. There's enough evidence to reject the claim that the waiting time for dinner is 1 hour. So that was just kind of like a real-life example take on it. And let's get to more practice problems. So again, I said I'm going to only do data one way. I'm going to use the TI. This problem gives us data. So find the average, find X bar of all this data. And that's going to be your second step after writing down the hypotheses. The model we've asked again, listed below are their weights. Assuming the weights have a standard deviation of that, use 0.05, significant low. Test the claim that bats comes from the same population. Test the claim that they have a known mean of 1.8. So we're testing if they have a mean of 1.8. That's an equal to. So our alternative would be not equal to. That's my claim. So first I'm going to write down what I do know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 for N. They give us sigma as 0.30. Alpha is 0.05. And we'd have to calculate X bar. So I'm just going to do this whole thing in the TI. Save some time and length of this video. First thing I'm going to do is go to the top, clear, enter. Type it in. 1.2, 1.4, 1.6, 1.6, 1.6. Okay, 15 data values. Good. Get out of there. I'm just going to run the test using data from list 1 and with a mean of 1.8 and a standard deviation of 0.3. Excuse me. We also have a two-tail here, so because our alternative was not equal to, calculate that. So we get z equals negative 1.1189. And we get x bar is 1.71. Actually, this goes to the 10th place, so I need to go to the 100th place, 1.713. Not 1.71, sorry. 100th place, so that rounded is 1.71. And yeah, p-value, 0.26. That p is definitely greater than alpha, so we're going to fail to reject the null. So there is not enough evidence to reject the claim that the stats come from the same population with a known mean of 1.8 grams. Does it appear they're from the same population? Sure, can't say they're not. That's what our hypothesis said. Okay. Casio users, you'd type these numbers in your list or just add them up and divide by 15, your choice, whatever you need to do to get X bar. Round it properly to the 100th place. Plug it in the formula to get your test statistic. Find the area. So there's a two-tail. So we find the area to the left. It's a two-tail. We find the area to the left because it's negative. It's less than the center. And then we double it. So I'll go ahead and do that. Negative 1.12 is 0.1314. And I double that, and I get 0.2628, 0.2632 from the TI. All right, that's it for today. So this was hypothesis testing with the mean with sigma known. Next time will be hypothesis testing with sigma unknown.